Good morning, everyone. I'm definitely having a hard time waking up this morning because I got here midnight last night. So if I fall asleep during my talk, you know why. As I understand, my task here today is to get everyone on the same page in terms of some basic understanding of mantle melting or magma generation processes, primarily giving you the framework of melt generation or partial melting beneath mid-oceanic ridges, and then discussing how that framework differs or what are the similarities with that framework with magma generation processes in subduction zones. So again, I'll try to keep the talk at a very basic sort of advanced spectrology type level so that we are all on the same page, okay? But what I thought I would do first is ask you guys the question, why is magma important? This is especially important because I may fall asleep, so if you guys know what we are talking about, we'll be fine. So this is actually a question for you guys. Why do we need to care about magma generation processes, or why do we need to know about magma in general? What is it good for? I ask these questions to all my grad students and even the undergrads, so I may as well treat you like that. If we do not know why we want to study this, there is no point figuring out. How it works. Any takers? Bill.
Release heat from the interior.
Okay, that's one.
Segregate the earth.
Segregate the earth. Yes, Ken.
We need to know how fast to run if you live near Mauna Loa.
Yeah, that would be a good one. So I have a list myself, and I just want to see whether my list is same as yours, and I'm pretty sure there will be more reasons to care about it.
Raj, we're waiting for the students.
Climate.
Create new crust.
Create new crust. Anything else? Mass transfer, creating crusts, or yeah, the same, more or less. Differentiation of the earth. Yeah, good. Yeah, that's how I earn my living. That's for sure. That's there. Okay, so let me show you guys the list I have, and I think you guys pretty much mentioned all of that. Crust formation. So in my mind, at least, this is at least the melting process or partial melting process is the single most important process by which our planet continues to chemically differentiate. Okay, and formation of crust. I think this did not get mentioned at least explicitly, but mobilization or concentration of key trace elements, formation of ore deposits. Again, it relies on partial melting process. Basically, scavenging trace concentrations or trace elements from a vast region and then eventually mobilizing and concentrating. Mantle degassing, so release of key volatile species like water or carbon dioxide from the interior. So Mark, you mentioned long-term climate, that's here. Carrier of heat, that got mentioned. And I would plug in life here as well because I think it's critical for at least origin of some deep life in terms of how the heat is released and where it's released and so on. Magma is also important, not only this broad scale differentiation, but also in terms of many of the properties in the interior of our planet as well. What are some of those? Why do we need to know where melt is generated, where magma is generated, and what are the various properties that magma might influence in the interior? Viscosity.
The nature of the asthenosphere.
Nature of the asthenosphere. Anything else? Attenuation. You're just giving me confidence. I think I have these words in my next slide. So I'm just feeling relieved here. Anything else? Say it again. Density. I may not have that. Anything else? Okay, we'll see. So I have rheology as a sort of like a broad property. Then various physical properties like seismic wave speed, conductivity, viscosity, attenuation, density. Depending on where magma may or may not be stored, these various properties may be affected. And then finally, before moving on to the actual framework of magma generation, what does magma actually tell us? So we know magma erupts on the surface, but what are the different information we can gather by studying the eruptive products? Or what are the main ones? At least I have two. It tells us about the composition of the interior, so we can sort of use it as a remote sensing tool by studying the composition of magma. What's the composition of the interior of the planet? Not only in terms of the major element composition, it also in terms of the trace element composition, including volatile elements. And then you can also study magma. I probably won't go into details, but there are different thermometry or barometry you can devise out of magma chemistry to figure out the temperature of the interior or the depth of magma generation or melt segregation, right? So these are some of the things you can learn by studying magma. Okay, so then to sort of lead to the actual talk, where on earth we get magma? So what are the different tectonic settings where we get magma? Again, this is sort of 101. Beneath mutationic ridges or at mutationic ridges, at some off-axis melt generation settings, in ocean islands like intraplate settings like Hawaii or Samoa. Matt is back there somewhere. At volcanic arcs, we get magmas. Also, we get basaltic magmatism or some weird kind of magmatism also on continents, right? So these are some of the various settings where we may be getting partial melt generation. And the process of partial melting is the key because all the magma regeneration pretty much happens because of partial melting in the mantle. Another thing that you notice is if I'm correct about delineating various locales of magma generation, they're all relatively shallow compared to this whole sort of more like a whole earth, whole mantle cartoon that I draw here. That's not to say that there are no other depth ranges where melt generation may take place. There definitely are, but clearly it's a relatively shallow phenomenon. And that also actually is telling us something, why melting is relatively shallow features of the mantle, and we'll come back to that. Okay, so what is melting? First, again, this is 1-1, I understand, but I think it's good to tell especially the students what melting is. So melting is basically a phase change. It's a process by which you break down a crystalline product with long-range order, repeated unit cells, to something which does not have a well-defined crystalline structure. It does have short-range orders, so it's not like all bonds are broken, but some bonds are retained. So it's a liquid. So it's a phase change. And as you will see, there are some similarities and there are some differences between melting or a simple phase change for a pure substance, or I would call it like a one-component substance, to more complex substance that we will be dealing with for mantle melting. So if we do melting of a pure one-component substance, and again, this is just my hand-drawn thing, and it's I hope it's right, but it's simplistic. So if you melt something like quartz, let's say, or you can melt ice, for example. If you supply heat, that's shown as on x-axis, and temperature, melt fraction, or the extent of melting F, and entropy S. If you do a pure one-component melting, you first increase, as you put in more and more heat, you increase temperature, all the way up to the melting point, which I would call it a solidus, or the first melting point. And then as you supply more and more heat, temperature will not increase, but you will convert more and more solids to liquid phase as the phase change is occurring. And your total melt fraction is gradually going to increase from 0 all the way to 1. And when it reaches 1, I would call that point the liquidus, or the final melting temperature. Okay. Now, in case of pure substance or one-component substance, there is no temperature difference between the solidus and the liquidus. It's the same, whereas the melt fraction is increasing. And the entropy, which actually another way to think of melt is it's a higher entropy phase rather than the solids, which is a relatively lower entropy phase. If I go back to my previous slide here. Again, melt, high entropy, more bonds are broken, low entropy, all bonds are together. So the entropy initially increases with temperature increase for solids, but then it increases much more rapidly as melt is forming, as you are converting more solids to liquid. And then again, once all the solid is transformed to liquid phase, again with increasing heat content of the system, you can increase entropy as you go to a higher temperature. Okay, so this is sort of the view that I would like you to keep in mind, thinking of a one component system melting or pure substance, melting of ice, melting of quartz, melting of any pure end member mineral you can think of. Take your favorite like forsterite or phyalite. If it's pure substance, that's how melting would work. However, as you will see, melting is not exactly like this for the mantle. But before I go to that, if you are wondering how the melting reaction or the melting curve, so to say, will appear on a pressure temperature space, as you saw that it's the entire conversion of solid to liquid happens at one temperature. So you can go from an entirely solid substance to an entirely liquid state at a fixed temperature or at a fixed pressure, right? So the reaction, there would be a volume change of reaction associated with something like this, a pure quartz melting solid to liquid. So there is a volume change of reaction. So volume of the liquid minus the volume of solid, and the entropy change of the reaction is entropy of the liquid minus the entropy of solid. In this case, for a reaction that appears like this, meaning in a pressure temperature space, I would call it has a positive slope. Both the volume change of reaction and the entropy change of the reaction, both are positive. Okay, and I'll show you quickly in the next slide. That's why the slope of this line, the dp dt of this reaction, is positive, because it's basically a ratio of these two properties. I would probably skip through this mostly, but just to again remind you, especially for the students, you can treat this thermodynamically pretty much starting from the first law of thermodynamics. So internal energy or change of internal energy is defined as heat and work. du is Q, heat and work done, W. You can express it as TdS minus PdV. So it's the mechanical type of work, and that's the entropy change times temperature. You can also express Gibbs free energy as the state function, where it would be U plus PV minus Ts. You can expand it, plug in the value of du here from this equation, and get dg, or change of Gibbs free energy, equals to minus S dt plus volume times change in pressure. And pretty much from that equation, you can then derive, if you are worried about change of Gibbs free energy of that reaction, similar to the reaction I showed you, like melting of quartz, then it would be the delta S of the reaction dt, delta V of the reaction times dP at equilibrium. When the solid and the liquid is coexisting, there is no change of Gibbs free energy of reaction. So d delta G of reaction is 0. So if you plug in 0 here, you can figure out that then at equilibrium dP dt is delta S reaction divided by delta V of reaction. And this is very important for understanding melting. This is called the Clapeyron slope. dP dt is equals to del S over del V. Now for the reaction I showed you, melting of quartz, again, both delta S of reaction and delta V of reaction, both of these are positive quantities. As a consequence, the Clapeyron slope is greater than is greater than 0. It's positive. And there are exceptions to this, and we will come back to this feature. So take a note that in my example so far, dP dt is positive, but it may not be always positive. And I'll ask you later when it's not positive, how can it be not positive? However, to reiterate, for a fixed pressure, melting of a pure substance happens at a fixed temperature. So again, in a pressure temperature space, you can melt from or go from solid to liquid. You can do the phase change isobarically, meaning at a constant pressure at a fixed temperature, or you can do isothermally just by decompressing the solid and take it to the liquid state. But all of these two no matter which one you do, again, the melting, entire conversion of solid to liquid will happen at one temperature or at one pressure, right? Now the question is that the case for mantle, or is that the case for any natural substance that we would be dealing with? Actually, it's not the case for melting of an impure substance, or I would call it any system with more than one component, okay? And again, you can show it in a variety of forms. I am showing it with pressure and composition as the x-axis pressure, as y-axis. This is actually an upside down figure in my mind. Pressure is not higher as you go deep here. Pressure is higher as you go up. So this is deep. This is higher pressure. This is shallow. It's lower pressure. So as you add a component, any component, to your original component, the melting loop is created. In other words, as you decrease pressure, you cannot go from an entirely solid state to an entirely molten state at a fixed pressure. You will have to go through a range of pressure, right? So this is the solidus as your substance is decompressing, coming from greater depth to shallower depth. It hits this line here, that's the solidus. So you first create a melt of this composition, and you have a solid of this composition. As you continue to decompress your impure substance, the solid composition changes along this line, liquid composition changes along that line. Finally, when the liquid composition comes here, it's exactly the same as your initial solid composition. That's where your impure substance is completely molten, okay? So you go through a loop where melt and solid both are coexisting over a range of pressure. That's unlike my cartoon phase diagram shown here for a one-component system, right? And you can show a similar diagram, which is more commonly shown in textbooks. If you plot temperature versus composition, you can also have a phase field where you have solid and liquid coexisting. So the temperature difference between the solidus and the liquidus is non-zero, or the pressure difference between the solidus and liquidus is non-zero for an impure substance, for any system with more than one component. Okay, and that sort of is the main framework for understanding magma generation in the mantle. So again, now I'm showing you a very similar plot as my original cartoon. Sorry, the labels are missing here. So this is temperature increasing to the right, pressure in this case increasing as we go deeper. You now have a solidus and you have a liquidus, which is separated in pressure temperature space. In other words, if you increase temperature or if you decrease pressure, you are not going to go from an entirely solid to an entirely liquid state at a fixed temperature or a fixed pressure. You will have to go through a phase field where two phases are coexisting, the solid and the liquid. So you have a solid path and then you have a solid and liquid path together. And also shown here are these dotted lines. These we would call contours of constant F or constant melt fraction. So in other words, as you go from the solidus to the liquidus, your amount of melt in the system is gradually going to increase from here to there or from here to there. Okay. Actually, for our planet, decompression melting is much more important. So although you can melt both by increasing temperature or by decreasing pressure, for our planet, it's the decompression melting that's much more important. Delta P, or change in pressure, is much larger compared to the change of temperature. The lateral temperature gradient, at least in bulk part of our mantle, is much smaller, although there could be some debate about it. Locally, you can have strong temperature gradient. And beneath mid-oceanic ridges, especially, decompression, this rise of your mantle parcel happens primarily owing to plate spreading. And there are other ways to decompress mantle. We are probably not going to go into those details, but you can have some thermal boundary layer heating from below. You can drive a more active upwelling rather than a passive upwelling here. That's shown here. So anyway, so you have decompression melting dominating the melting process beneath mid-oceanic ridges and also beneath hotspots or intraplate ocean islands.
Raj?
Yes.
Can you discuss why the slope of the adiabatic changes?
Yeah, I'll come to that. Yeah. We'll talk about that. So yeah, that's a good point. As Matt is asking, why is this path of this solid adiabat has a steeper slope than this path from 2 to 3, where solid and liquid they are coexisting? Why is that slope somewhat shallower? And it's actually fairly important how we understand decompression melting, especially beneath ridges. And yeah, I'll come back to that. So how does decompression melting work? Again, there are many ways to treat this. And this is a very simple calculation after Mackenzie and Bickel, 1988. You can treat, let's say, a parcel of the mantle of certain diameter or radius, in this case r. It has a density rho 0, and then it's traveling with a velocity v upward. Okay, you can then define what we would call it this dimensionless number, Peckley number, which is velocity times the length scale of your mantle body or any impure substance you are dealing with, divided by the thermal diffusivity kappa. So it's basically, this ratio is nothing but the importance of heat flow relative to advection. The conductive heat flow or heat loss or heat gain of this body relative to the advective heat loss or heat gain of this body as it's rising. Okay, so material velocity v, length scale L, thermal diffusivity kappa. If this ratio is greater than 1 or much greater than 1, that would tell you that advective transport of heat is much more important than the conductive transport of heat, either gain or loss. Whereas if the Peckley number is much less than 1, then conduction would dominate. For our planet, for Earth, the Peckley number is around 100, especially beneath mid-oceanic ridges. If you take the material velocity, upwelling velocity of the mantle around 5 centimeter per year, length scale of around 100 kilometer or so, thermal diffusivity 10 to the power minus 2 centimeters square per second, you see that it's a dimensionless number and it's around 100, or it could be more. So unless...
Excuse me, where does the length scale come from?
So it's the way to think about it is what domain of the mantle is undergoing upwelling. What is the length scale over which heat has to diffuse in or diffuse out? So you can treat, if you think that the domain that's undergoing upwelling is a tiny blob of very, very small diameter, then this argument may not work. Then the length scale may be too small and conductive heat flow into the body or out of the body may dominate. Whereas if you are interested in a broad scale upwelling of the mantle, which is sort of the case beneath mid-oceanic ridges, this length scale is much larger, and as a consequence, Peckley number is much greater than 1. I don't know whether that exactly answers your question. But
Can I get you to commit to the length scale? So you've got two in the problem here. One is the width of the plate boundary, the width and rate state, and the other is the thickness of the plate state. So which is the right one?
So the question is, when I'm dealing with the length scale here, is it the thickness of the lithosphere, if I understand correctly, or the length of the ridge? Is that? Or the width of the ridge? I would guess in this case it's the width of the ridge, but you correct me if I'm wrong.
Oh, that's fine. I just think Kent is asking you to go geological on.
Oh yeah. So in this case it's the width of the ridge that so it's the lateral length scale rather than the thickness of the lithosphere. Okay, so in this case, it's Peckley number of 100. So I can upwell a piece or parcel of the mantle much more quickly than it would lose or gain heat from the surrounding or to the surrounding. So the decompression melting in this case then would be adiabatic, or Q equals 0, meaning my mantle is rising fast enough that it's not gaining heat from the surrounding or losing heat to the surrounding, or Q equals 0. So not only decompression melting is important, the decompression melting that we are dealing with is, for most part, we can approximate it as an adiabatic process. But remember, it's an approximation. There could be scenarios where the Q is not exactly 0. You can think of, as I said, very small diameters where it may not be exactly adiabatic.
I mean, because there's still a bit of grumbling about this. You know, for students, it's important to realize that what the Pegler number is a ratio of timescales. It's a ratio of the diffusive timescale and the ratio
of advective timescale. That's right.
What we're seeing there, and we had a discussion about this yesterday, because we plug in the Stokes velocity for V here, you can recover the Rayleigh number.
Right.
But then it comes down to these length scales being matched or not. Well, all of a sudden you get a factor of 1,000 or a factor of 1 coming out. But really, this is just timescale ratio.
Right. And I was not going to go to Rayleigh number and the other dimensionless numbers because I believe there would be other lectures on that. But the other thing to think about is what's the viscous drag, what's the viscous resistance of upwelling to that vective, and that's sort of the Rayleigh number. And you have a critical Rayleigh number that would allow convection, which I believe is 10 to the power 3. Correct me if I'm wrong. If for our planet, 10 to the power 5 to 10 to the power 7 is the Rayleigh number, so we have convection. Okay, so the viscous drag is not big enough to impede convection and upwelling. Okay. Okay, I think I sort of can skip this, but now that we sort of worked on the thing that it's an adiabatic process that we are dealing with, decompression melting. From a thermodynamics perspective, then I would say Q equals 0. Adiabatic decompression melting can be described from pretty much the first law of thermodynamics as this change of internal energy as Q plus W, Q minus PdV, where Q would eventually be can be 0 and minus PdV. If you plug in enthalpy, definition of enthalpy, which is defined not in a differential form but in an absolute form, H equals E plus PV, then DH equals DE plus PdV plus VdP. You can then, and then Q plus VdP, where did it go? Yeah, so then I can plug in this here, and TdS plus VdP DH equals, and then equality sign would apply if I treat my adiabatic decompression as a reversible process. It would, DH would be less than TdS plus VdP if it's an irreversible process. And again, for most part, we treat the partial melting, decompression partial melting, as not only an adiabatic process, but also a reversible process. In other words, you can break down the entire path of upwelling into very, very small segments, such that if you, once the parcel decompresses a small fraction, it creates a tiny bit of melt. If you compress that parcel with that amount of melt back to its original pressure, that melt, that tiny amount of melt will freeze back in, and you will have the same amount and same composition of the solid. And as long as you can break down that entire path of upwelling to these tiny fractions, you can treat the process not only as an adiabatic process, but also as a reversible process. But again, I want you to know this is also an approximation. And if you do that approximation, then your process is reversible and adiabatic. In other words, change of entropy is also 0, or it's an isentropic melting process. So the only thing then for minimization of enthalpy, which would tell you the equilibrium state of melting, is it relies on change of pressure. So it's pretty much the change in head of pressure that dictates or that sets up the amount of melt generation, because it's an isentropic process, it's an adiabatic process. And again, these are sort of the working definitions of those symbols here. Okay, so if I quickly go back to this diagram now. So now we have this path, solid path, an adiabatic path, an isentropic path, presumably, and increasing or decreasing in pressure, rising, hitting this point, which is the solidus. As soon as it hits this point, it starts to create some fraction of melt. And as the mantle rises more and more, it melts more and more as it passes through these constant F contours, and it melts more. So you have two different lines to deal with here. One is this line here, which is the solid adiabat or the mantle adiabat path. Another is this line, the solidus. The location of both this as well as this, both are very critical in terms of figuring out what's the initial depth of initiation of melting. And pretty much many petrologists, including myself, we earn our living just to figure out where this intersection is. Where this line is, what are the different factors that can move this line? What are the different factors that can move this line? Okay. So that's what this is here. And also, the other thing is the isentropic decompression, as you can see from this first law of thermodynamics, because TdS is 0, change of entropy is 0, du, or change of internal energy, is minus PdV. Or in other words, isentropic decompression causes upwelling mantle to do work on the surrounding. So that means internal energy would drop with increase or with decrease of pressure, and temperature would drop. Okay, and that's the reason that solid adiabat actually is not exactly isothermal. It's pretty steep, but it has a slope of around 0.5 degrees C per kilometer, or around 15 degrees C per gigapascal. So just work in your head, 1 gigapascal is around 30 kilometers, roughly. So that's the solid adiabat slope. dt dz is 0.5 degree C per kilometer. And then the other line that I wanted you to worry about is the line, the solidus, or the slope of the solidus. dt dz of the solidus is around 3 to 4 degrees C per kilometer, at least in the shallow mantle. Okay, this is good news. The reason this is good news is if you did not have this number lower than this number, you will not be sitting here. In other words, there will not be cross generation by decompression partial melting. There will not be origin of life, pretty much. Okay, we will be on a different planet if these two numbers were flipped. Okay. However, this number is not constant. The reason I'm putting down a number 3 to 4 degrees C here is that's what matters for the shallow upper mantle melting. But with increasing pressure, the solidus actually in PT space, it sort of bends like this. And that's because of the reason, again, if you recall, dp dt of the solidus, the Clapeyron slope is del S over del V. The delta V of melting reaction approaches 0, or in other words, the density contrast between the liquid, the partial melt that's produced, and the solid that's melting at higher pressure is relatively small. As you go to higher and higher pressure, as a consequence, the del S over del V becomes large. Okay, so the solidus bends around. Okay, so again, this basic framework of decompression melting, isentropic adiabatic decompression melting, works for, of course, works really well for mid-oceanic ridges where melting is aided by plate spreading. You have a corner flow, you have a passive upwelling. It actually works, reasonably well and almost equally well for understanding melting or melt generation in intraplate settings where the cause of upwelling may be different. There may be other active upwelling sources or some sort of thermal anomaly driving the convection or driving the upwelling. However, it's still the decompression melting. The chief difference would be the head or the height between that intersection of the solidus and how far your mantle parcel can travel to continue to melt may be limited because your melting setting is actually happening below a relatively thick lithosphere, which is not participating in convection. In other words, it's hindering upwelling to a relatively greater depth. But other than that, it's basically the same decompression melting scenario. Oh, I actually forgot to address, Matt, your question, and I can do it here. So again, as Matt was originally asking, why is the slope of this line, the solid adiabat, steeper than the line, the adiabat of the solid and melt system together? Why is this shallow? Why are you cooling after you intersect the solidus and you are continue to upwell? Why are we cooling as you are upwelling? Any takers from the students? So the mantle actually cools as it upwells. That's true for solid assemblage as well, because there is a drop in internal energy and drop in temperature as you are decompressing. But that rate of cooling is somewhat faster per kilometer travel after the intersection of the solidus. It's actually fairly simple if you recall the fact that we set up our framework of decompression melting as an adiabatic process, right? Meaning no heat is coming into the system, no heat is going out of the system. Meaning when I say system, it's the box of the rock with some partial melt in it. However, in order to partially melt your system, you'll have to supply latent heat of fusion, right? You'll have to melt the rock. Where would that heat come from? It has to come from within the system, right? There is no other heat source. And as that heat comes from within the system cools, right? It's actually very simple. So for example, when it snows, okay, it feels, after it snows, it feels warmer, isn't it? It's exactly the same analogy why the mantle cools after it intersects solidus, right? You'll have to supply that latent heat of fusion, and it's coming from within the system. As a consequence, the system is cooling.
I don't know if this was saying for a unitary system, then it goes right up to solidus.
For one component system, yes, that's right. Then it goes along the solidus until you convert all the solid to the liquid, then it departs from the solidus, right? Yeah. But I sort of skip that part. So this is sort of elaborated more in this diagram. So again, pressure increasing downward, temperature increasing to the right. You have the solid mantle adiabat shown here in red with a steeper slope, and then the mantle starts to melt, and the system follows a different adiabat, solid plus melt adiabat, which with a different slope. So if you extrapolate this solid mantle adiabat with the same slope all the way to the surface, without worrying about the fact that now your adiabat is a different slope, if you follow the same slope, this temperature where it intersects the surface, we define it as mantle potential temperature. Okay, and you will probably hear this parameter keep coming back in various lectures, because this is a reference temperature we use for referring to what's the temperature of the mantle. The reason we do that is, as you see, that with the solid mantle adiabat increasing in temperature as you go deeper and deeper, depending on who you talk to and what sort of processes they are interested in at what depth, you may be referring to different mantle temperatures just because you are at different depths or you are considering different processes. However, if you just extrapolate the solid mantle adiabat all the way to the surface, now you have a common point to talk about. Okay, so the key thing is, if the mantle potential temperature is low, then that means the solid adiabat is cooler. What that would mean is you will be initiating the partial melting process at a shallower depth. Whereas if the mantle potential temperature is higher, your solid adiabat is shifted to higher temperature, and the intersection of the solidus and the solid mantle adiabat would occur at a greater depth. Okay. So, but again, what I show here is two different temperature difference segment. One is the difference in temperature with respect to the extrapolation of the solid mantle adiabat and the melt plus solid adiabat, which is this delta Tf here. And another is the temperature difference between the solidus and this point, delta Tx. This delta Tf is basically a function of amount of melting, extent of melting that takes place at that depth, F times heat of fusion to melt that amount of solid divided by heat capacity at constant pressure, Cp, whereas this delta Tx is directly proportional to extent of melting and dTdF, which is the inverse of isobaric melt production as a function of temperature, right? Assuming that the melt productivity isobarically is constant. Of course, it can be nonlinear, but in this case, we are assuming that it's linear. In other words, the constant F contours are equally spaced between the solidus and the liquidus. Okay. So keep these two numbers in your mind, delta Tf and delta Tx. I'm sort of going the other way now. Pay attention to this equation here. Now, if you multiply P0 minus Pf, which is the initial pressure of melting and the final pressure of melting, wherever this endpoint is, the difference in this pressure times the dT/dP of the solidus, which would give you this entire length all the way up from here to there. And if you subtract from that that same P0 minus PF minus dT/dP of the adiabat, you will get this little length scale here. That's equal to this temperature difference, right? So in other words, this quantity here equals to delta TF plus delta Tx. If you rearrange this, you get this parameter F divided by the entire pressure head of melting, which is equal to the slope of the solidus minus the slope of the adiabat, enthalpy of fusion divided by heat capacity at constant pressure, and dTdF. Okay? Why this parameter is important is this is the parameter that tells you how much melt is actually produced as a function of upwelling, okay, as a function of decrease in pressure. And you can calculate that if you know this, and that. The first one, the dT/dP of solidus, I would argue we know based on laboratory experiments. We can conduct experiments in the lab and figure out the slope of the solidus. So we know that number. And I showed you that number, which is like 3 to 4 degrees C per kilometer. We can calculate this number as well. I didn't go through that rigorous calculation here, but it's again around half a degree per kilometer, around 12 to 15 degree C per GPa. We can approximate this based on some, again, laboratory data, the heat capacity, the enthalpy change for fusion. We have this, again, from laboratory measurement. We can also constrain dTdF or dFdt from lab experiments. So we have this, that, and we can calculate this. So we know how much melt can be produced per increment of pressure decrease. And this is pretty cool because we know for a reasonable range of mantle potential temperature of around 1300 to 1350, and the knowledge of our mantle solidus, this intersection takes place around 60 to 70 kilometer deep beneath mid-oceanic ridges. And the melt productivity is such that if you initiate melting that deep, you create F sufficient amount so that your crust that you produce, that the thickness of the oceanic crust ends up being 6 to 7 kilometers. So it's just a factor of 10 less than the initial depth of melting. And that's very consistent. We understand the thickness variation of our oceanic crust pretty much based on a relatively narrow range of variation of mantle potential temperature and the knowledge of this solidus. There are, of course, details we always worry about in terms of the exact chemistry of mid-oceanic ridge basalt, whether to match that we need something else other than peridotite and all that. But as a baseline, mantle melting of peridotite by decompression can produce this 6 to 7 kilometers of oceanic crust. And
Why 10% partial melt?
Say it again, sorry.
This amounts to about a 10% partial melt, right?
Yes.
And why does that number come up over and over again?
So yeah, if you divide by the total amount of melt that can be produced by this decompression process, if you know the melt productivity and the total volume of the mantle that undergoes partial melting from that 60 to 70 kilometer step all the way to the surface, the fraction you get is around 10%. And again, of course, there is a variation depending on mantle potential temperature. Some people would argue it's more like 7%. Some people would argue it's more like 10 or 11%. But it correlates with the chemistry of melt. And you'll see I'll show some of that if I have time. But yeah, the enrichment and depletion of the magma composition. Yeah.
Does it matter what depth the melt actually separates from the solid as it goes up?
It doesn't matter in terms of explaining the crustal thickness. It matters in terms of explaining the average chemistry of the mid-oceanic ridge basalt. And you can also see chemical indices that I'll show you that some mid-oceanic ridge basalt compositions will argue that they are actually a relatively lower degree melts, shallow melts, because the mantle was colder, or relatively greater extent of melt because they have different chemical signatures. So yeah, explaining the mid-oceanic ridge basalt chemistry would argue whether it melted more or melted less as a consequence where it segregated exactly. I'm not going into how to figure out exactly at what depth the melt segregates because I think I won't then have time to go into subduction zones. But yes, Roberta.
I think this is anhydrous situation, right?
That's true.
So it's worth just pointing that out.
Yeah. It's anhydrous, it's non-carbonated, and no volatiles, no heterogeneities of any other sort. This is melting of a garden variety mantle peridotite, fertile mantle peridotite. Things will change if you add other impurities, but we'll come back to those.
Question?
Yes, sorry.
So in this framework, what would you need to change in terms of the mantle potential temperature to get twice the thickness of the crust? This order of magnitude.
Twice again. I don't have that number in my head. Again, the question is what increase of mantle potential temperature will there have to be if you twice the thickness of oceanic crust? Maybe like 200 degrees. Is that?
I think that's about right.
That's sort of the number I have in my head, but yeah, I think so. So if you go from 1350 to 1550, you can double probably the oceanic crust thickness. Again, and that's again what is shown here schematically. For a colder mantle, you will intersect the solidus at a shallower depth, and then as a consequence, this triangular regime where the melt generation will actually take place is a smaller triangle, whereas if the mantle potential temperature is higher, the ascending mantle is warmer. As a consequence, it starts to melt deeper, and again, it's anhydrous melting, but that anhydrous melting or the solidus is now deeper, and your melt generation is taking place over a much larger volume in a two-dimensional cross-section, a bigger triangle. Okay, but again, Roberta, just to go back to your point, you can expand this triangle by adding other stuff to it as well, like water or carbon and so on. So you can expand this triangle by not increasing temperature, but by changing the composition of the mantle, basically.
Raj,
Yes.
how about whether the melt is heavier than the solid and that sort of thing? Does that play a role?
In this sort of scenario, I think the question is, does it matter whether the melt is heavier than the solid or not? Of course, it would matter if melt was heavier, it would not segregate very easily and you wouldn't have the crust. But the depth range, I believe we are dealing with in case of decompression melting, or even with a reasonable amount of volatiles and so on. It's not that deep, or the composition of the magma we are producing by such a process is not such that the melt would be denser than the surrounding mantle or the solid. So melt would be buoyant. You'll have to go fairly deep, almost to the transition zone, to have those scenarios in play. So maybe in a very hotter Earth, maybe ancient Earth, Comatite generation and all that. Sinti wrote about it.
That would not be true in a higher temperature.
That's true. That's what I said. If you go to ancient Earth with much higher mantle potential temperature, you can push this melting boundary, the intersection of the solidus and the adiabat, to much greater depths. As a consequence, the melt density may be much different. But I'm talking about sort of the melting scenario for the ongoing differentiation of the planet, meaning present day. Yeah, then it's not an issue. Thorsten.
Could you maybe explain again why this thing is a triangle?
Yeah, good question. Why is this a triangle? Anybody knows why is this a triangle? Okay, so the thing that happens is what is shown here is sort of the ascending mantle adiabat, and then the melt solid adiabat is slightly cooler. But eventually, as you go up, farther up and up, depending on which flow path, so again, I probably didn't explain these very well. So these are various flow paths of the ascending upwelling mantle. So a mantle parcel here would follow this line, a mantle parcel here would follow that line, and so on. So depending on which of these two paths you are following, eventually at some point you will start to cool off because the conduction would start to dominate. And depending on which path you are following, if you are in one of these middle paths, you will go up all the way here and then start to cool off very shallow. Whereas if you are in one of these, you will cross the solidus but then switch back to a cooler temperature with respect to the solidus at a deeper depths. As a consequence, in a two-dimensional cross-section, what you have is a triangle. But of course, it's really a prism. You go along the ridge. I'm just showing a cross-section here. Yeah?
And also, people were worried about the thickness of the crust for different temperature mantle. It's quite popular.
Yeah, and that's what you sort of shown here. See, the oceanic crust is much thicker here.
So it seemed like that there were quite large uncertainties in the details between the thickness relationship and the thickness of the potential temperature. Could you maybe comment on if that's true and what the major uncertainties are? So there were a bunch of papers where Mackenzie Bigel was criticized on what seemed like fairly fundamental level, such that some of these factors have pressure dependence that wasn't included in the actual overburden changes and things like that.
Right. So the question is the relationship between decreasing or increasing mantle potential temperature and as a consequence the change of the oceanic crust thickness fairly well understood, or are there things that can complicate it? I think as far as my reading goes, I think broadly speaking, the correlation works. In other words, you have deeper melting, you create thicker crust. However, I think in terms of the oceanic crustal thickness, oftentimes we are dealing with like the eruptives and the total crust produced by that process. I think there are issues with melt segregation and what amount of melt actually makes into the ridge and eventually erupts at the ridge, and how it actually then manifests itself on the crustal thickness. So I believe there are complications in terms of as you produce a deeper melting triangle or broader melting triangle, in terms of how the deeper melts sort of converge all the way to the ridge axis. It's easier when the melting triangle is 60 kilometers deep, the base is here. But if you make the melting triangle base all the way to, 150, 200 kilometers, you'll have to segregate melt from a much larger region of the mantle. And that's one of the factors I think can be fairly complicated. I don't know whether you were commenting on something else. Doug?
Yeah, I think there is some debate about like the degree of temperature variation along the mid-ocean ridges.
Oh, along the ridges, okay.
And how that relates to the crustal thickness variation
Yeah.
along the mid-ocean ridges. Because some of the models, like Langmuir's model, originally had 100 or 200 degrees
Along the ridge, yeah.
variation, and then other models have smaller variation.
That's true.
So,
That's true. I think
you might have some comment.
Yeah, I was going to show you some of the chemical variations that people talked about in terms of along the ridge variation and how it relates to temperature. And this is actually one that how do we actually reconcile, everything I told you so far is that, okay, hotter mantle melts deeper, produces more melt. Colder mantle melts shallower, produces less melt. It's a theoretical framework, but does that make sense with respect to the chemistry of mid-oceanic ridges? And I'm just showing you one snapshot here, which is sodium content, Na8, don't worry about it, it's just fractionation corrected sodium concentration in mid-oceanic ridge basalts, plotted as a function of depth of the ocean floor from the sea level. So when the number is smaller here, that means the crustal thickness is small, you have a deeper crust. When this number is higher, that means the crust is thicker, you are reaching the ocean floor shallower. What you see here, that the sodium concentration, fractionation corrected, correlates positively with depth. What that means is, and at least how it's interpreted, is higher sodium abundance, because sodium is actually what we call it an incompatible element. So if you look at this equation here, concentration of any element, in this case sodium, in the liquid, divided by the concentration of sodium, in this case in the mantle source before melting, equals to 1 over F plus D minus F times D, where F is the extent of melting or melt fraction, and D is the bulk partition coefficient for any element under consideration, in this case sodium, meaning how sodium partitions from the solid to the liquid. If D is less than 1, then we would call the element to be incompatible. If it's greater than 1, it's compatible. In this case, sodium is an incompatible element, meaning it enters the melt phase. So if the extent of melting is more, meaning in other words, if F is larger and larger, as you can see from this equation, Cl, which is the concentration of sodium in the liquid, will be diluted. And that's exactly what you see. If you have hotter mantle, you will have more melting, because you are starting to melt deeper, and as a consequence, your mantle will go through that melt zone much wider, and you will melt more, your sodium will be depleted. Whereas if your mantle is cold, you will start to melt shallower, and as a consequence, you have much lesser headroom for your mantle to travel, you will melt less. As a consequence, your incompatible element abundance will be more enriched in the melt. Okay. So overall, I think it's broadly consistent with, and this is basically many different ridge segments that are averaged, normal ridges, hotspot influence margins, and so on. Broadly, it's consistent that more melting is aided by higher mantle potential temperature, less melting aided by colder mantle potential temperature. Cinti.
Maybe this is a question for also the seismologists, but when you actually do get the oceanic crust thickness, has anyone put from the seismology, put it together with this to see if there is the predicted correlation?
Yeah, that's a good, yeah.
I don't know.
To my knowledge, there has not been that sort of a global systematic approach, but Doug or someone.
I think one problem is the crustal thickness has not been measured by, say, active source seismic, not very many places along the ocean ridge system. I guess the other issue here is that some of the variation of the ridge height here is coming from dynamics or from temperature variations perhaps beneath the crust. So, so it's not just a variation of crustal thickness, but there is some suspicion that the crustal thickness seems to be more uniform than would be predicted by the linear model.
Which would mean there may not be as much of a temperature variation along the ridge, which Langmuir sort of claimed in his original.
Actually, the crustal thickness you would predict it's the hot end that you defined it should be thicker.
That's right. That's why.
It's opposite sort of what you suggested. So it's mostly buoyancy.
Which is opposite to what?
I thought you said that the far end was thicker crust.
No, this is thinner crust because it's deeper to the ocean floor. It's thinner crust. This is thicker crust.
But you need to test that.
Yeah. Well, one of the project ideas, I suppose, later down the line. Actually, sort of going along Langmuir's prediction, I think this is a paper from Langmuir and Forsyth. It's a sort of mini compilation. For slope, and they also claimed the spreading rate also matters in this case, right? Because if the spreading rate is slower, your mantle, as the mantle is upwelling, the mantle may start to cool too fast compared to its rise velocity. And if that happens, instead of getting a triangular melting regime, you may get this trapezium type of a shape, meaning you truncate the top of that melting triangle. And especially in this Arctic, I believe it's the Gackle Ridge, they claim that the ocean basin has this sort of narrowing sort of shape, and at this end, the basin width is much narrower, and they claim because it's colder here, and as a consequence, the melting triangle is truncated even deeper. Whereas, because it's a much slower spreading, if the spreading rate is very slow, mantle is not rising fast enough to undergo partial melting, and the flow lines are going out of that triangular region much deeper. Or on the other hand, if the spreading rate is faster, your cooling time scale would be slower than that of the upwelling time scale. As a consequence, you will continue to melt more, and eventually you will produce a wider ocean basin. And so it's the spreading rate, slow versus fast spreading rate, that can also influence the total amount of melt generated and also restrict or change the depth of the top of the melting column. Okay, so sort of the last half an hour or so, I'll try to go through quickly. Some of the differences are the frameworks, how the melting scenarios in subduction zones differ from what we have been discussing so far beneath mid-oceanic ridges. Okay, and what are the similarities? What are the dissimilarities? It's much more complicated in subduction zones. The flow pattern is different, and we cannot probably apply some of the exact setup here. But again, to go forward, contributions of mantle wedge flow, how that influences melt generation beneath volcanic arcs, contributions from the downgoing slab, which includes the mantle, the crust, and the sediment, the decompression melting of the wedge. Can we invoke similar adiabatic isentropic decompression melting scenario as we have set up for beneath mid-oceanic ridges in the mantle wedge as well? Or are there additional factors such as things coming off the slab and modifying the mantle wedge, and what are their relative contributions? Okay, so again, this can be probably an entire semester worth of lectures if I really do it right, but I'll do quickly in half an hour. So the key difference, at least in my mind, if you compare the chemistry of basalts at volcanic arcs and the chemistry of basalts at mid-oceanic ridges, the first one that probably stands out is the difference in the water content in the basalts. Okay? There are, of course, other differences, many others, trace elements, isotopes, and so on. But so MORB water content is sort of in the order of, and I do not have a reference, so I apologize for that, but it's around 1,000 to maybe 2,500 ppm. Some enriched MORB may have slightly higher water content, but ballpark in this range. Okay, and if we were just talking about that extent of melting, it's 10% partial melting or so on. If you divide these numbers by 10, because the mantle that produced this magma underwent 10% partial melting, you would come up with 100 to 250 ppm water content in the source, in the mantle that melted, right? And so it's ppm by weight. So the easiest way to think about it is sort of micrograms per gram, or you can divide by 10,000 to get weight percent water as well. In contrast to mid-oceanic ridge basalts, if you look at all the sort of subduction zone basalts, they have, of course, a range of water content. Recently, Terry Planck talked about how it's so constant. I'm less thrilled about the constancy of water content of subduction zone magmas, but broadly, of course, it's true that it varies somewhere between 2.5, 3 weight percent all the way to 7 weight percent in primitive or primary, near primary arc basalts. So how do we reconcile? How do we explain much larger water content of arc basalts compared to mid-oceanic ridge basalts? So of course, the first thing that people wondered about, we have more water in the arc basalts, so it must be the slab doing something, right? So it must be the clays and other hydrous phases that are entering the subduction zones along with those sediments or in the oceanic crust. They are breaking down, they are releasing fluid in the wedge, and of course they are making hydrous basalts in the mantle wedge, as contrast to more of a nominally dry melting scenario beneath mid-oceanic ridges. So the number that people worried a lot about is what's the depth of the top of the slab as it is subducting, what's the depth to the top of the slab directly beneath the volcanoes, the arc volcanoes, okay? What is that depth? The reason people worried about that depth is they were interested what happens at that depth to the rocks that are going down in subduction zones. Are they decomposing, devolatilizing? Are they releasing fluid? If they are releasing fluid, what sort of fluid? What are their chemistry? So this is sort of a compilation of height or the depth of the top of the slab surface from a number of volcanoes, from a compilation of Syracuse and Jeff Ebers, and as you can see, sort of the peak is around 100 kilometers. So on average, subarc depth, as people commonly call it, is around 100 kilometers, but there is a spread from all the way from 50 to almost 150 to 100 kilometers if you do the compilation. And there are different estimates, but again, broadly between the England et al. Study and Syracuse and Ebers, there is a broad correlation. Again, most of the arcs provide 100 kilometer subarc depth, but there is a range. Okay, so what people have worked on over the last 3 decades is to tease out in detail the phase diagrams of these complex lithologies, various types of sediments, ocean crust, altered oceanic crust, mantle that enters the subduction zones. What are their behaviors in these sort of depths, like sort of 100 kilometers, 50 to 150 kilometers? What are the different mineralogies of those rock types? What are the different types of devolatilization reactions and so on? And again, there are many literatures. I'm probably not doing justice to those. I'm just picking and choosing here. This is one phase diagram of a basalt water system. So in other words, these are morb, mutogenic ridge type basalts in the presence of excess fluid. What are the different mineralogies that are produced here as a function of, so this is pressure increasing upward, temperature increasing to the right. This is coming from Schmidt and Poli 98. The thing to pay attention to are these different colored lines that I have marked here are the breakdown lines of different hydrous minerals that can be present. Lawsonite, zoisite, amphibole, that would break down at different depths. Okay, and it also depends on the pressure temperature path of the subducting material. Okay, so depending on whether you are following a relatively cool subducting PT path or relatively warm PT paths, different minerals will break down at different depths. But typically for altered oceanic crust, it's a breakdown of amphibole, zoisite, and lawsonite that that are known to release hydrous fluids. Okay, at this sort of depth range, 3 GPa or so, 700 to 800 degrees C. You have similar things for peridotite water systems. People wondered about breakdown of amphibole, chlorite, or 10 angstrom phase, and so on. And based on all these experimental phase relations that have been determined in the lab, there have been more thermodynamic toolboxes that got created, like Parplex or Thermocalc and so on, which can also allow you to create pseudo sections or pressure temperature sections for stability of various hydrous or carbonated minerals and so on. And based on that, sort of late 90s, early 2000, people were putting together these models of at what depth different devolatilization reactions will kick in, which minerals will break down at what depth, and how water-rich fluids will be liberated from this downgoing slab in the mantle wedge. Okay, so the idea was hydrous fluids will come off the slab, will influence the melting properties of this mantle wedge, and that must be inherent to the magma generation at subduction zones or the chemistry of volcanic arc magmas. Okay, but one thing I will come back towards the end is you also pay attention to the fact that although hydrous fluids might be coming off the slab, the flow lines, which are shown here with these black arrows, also have a decompression component to it, right? So the flow lines are such that it goes up and then turns around in this cold nose part, and then the flow lines are parallel to the downgoing flow of the slab, right? So again, the question that I think remains a debate even to this date is what's the contribution of these decompression path in creating arc magmas versus the flux of these hydrous components that are coming off the slab and producing magmas. And different people in the community, continue to have different opinion, the relative contributions of these two processes. Yes, sir.
What's the reason the flow paths look like that? What's the evidence for it?
Good question. So the question is why the flow path has a shape like this that are drawn here like that, and what's the evidence for it? I'm not 100% sure whether I have answered to that. I mean, I believe, well, of course, this part is clear because I think there is some sort of a dynamic coupling between the downgoing slab in dragging the mantle down. There is a viscous coupling. Whereas this part of the flow path is subhorizontal to horizontal versus with an up-dip arrow, I think is somewhat more controversial, but I think it's partly owing to the shape of the deep crust and the lithosphere, the geometry of it. In other words, to fill the space all the way to the nose or this corner here, and then turning around as it couples. But I'm not 100% sure because different thermal models produce also slightly different temperature profile, and that influence the exact flow path that is expected. And I'll show you a couple of different examples where the isotherms look different depending on whether you assume an olivine rheology versus an isoviscous rheology for the mantle wedge and how that influences flow path. But yeah, sorry, we'll come back.
The marble cake formation, and then you can maybe improve the upwelling formation.
Thorsten.
In general, pressure that sucks things in. And now if you on top of that allow for reduction in viscosity,
right,
stress dependence, influx of water, then you get squishier material and you will modify these flow lines. So I think it's a fair statement to say we can model all kinds of things to these flow lines. But I think this sort of upward nudge is perhaps a robust feature, and then you can look at heat flow going along the
right,
arc.
right.
Because the heat flow will, of course, care about the spacing between the isolines. So if you have higher or lower heat flow, that gives you some constraint on how thin or how widely spaced these isolines are. And then you can turn it around and run a flow model and say, well, for this viscosity, I get sort of a hot or a cold nose, basically.
Right. But also, I'll probably come back to this, Thurston, but isn't it the newer models are also trying to decouple the coldest part of the nose from the rest of the mantle wedge? So, yes, the flow lines are influenced, but that cold nose is not dragged or anything. It's stable.
Yeah, so
right.
There's a bit of an issue in that most of these models are at least semi-kinematic. They're not fully dynamic in
No,
the sense that
it's pretty much all kinematic.
distribution you have would drive the flow, but usually you're shoving things in and prescribing at least part of the system, and that makes it required to have choices as to how much drag there is and what part you leave free, what part you leave
coupled and decoupled, yeah. Yeah, Adrian.
One added comment, and I agree with everything you said. The models also, I think, most of them have as a free parameter the depth at which you change your color.
Yeah, and I'll show. Yeah, I'll come to that.
And that's what would have to be observational constraint.
Right, right.
As far as I know,
it's not.
Yeah, because
You
on
said
the
it.
circle models, if you don't decouple the nose, then the hot corner just eats its way up to the surface.
Yeah. I'll I think I'm sort of we are going ahead, but I'll come back. Bill.
Just curious. I never have paid attention much to this. And I see the diagram has a brown layer at the bottom of the lithosphere called must be the LAB of peroxenite. Could you explain the origin of that, please?
Damn, you should be asking these guys. I think it's meant to represent that the lower crust is clinopyroxene dominated.
That's part of the crust.
I think these are cumulates. Would be my are cumulates.
Right?
What?
That should be the mantle lithosphere.
Although that should be the mantle lithosphere. I don't know why. Yeah, that's true. Yeah, I'm not sure why they put pyroxenites in the mantle lithosphere, but
if it was there, would seismologists...
Oh, could be there. I mean, you can have melt rock reaction or something producing that.
Would seismologists see it?
Say it again. Sorry.
If it was there, would seismologists see it?
I think it's fair to say that you could run the model so that you could put it towards the
You mean it would be a kinematic seismologist versus a dynamic seismologist?
I know you might get on, but I just want to make one comment. Just from an intuitive basis, if you have back arc spreading and you measure upwelling there, clearly there should be
decompression
there. Intuitively, it seems to me that the flow lines should just then go down instead of up because they'd be following the base of the lithosphere, perhaps. And so that's why, and this is kind of important because you have to go up in order to get decompression melting. So it's really kind of important to know, is this have any basis in reality, or is it, what are the, how loose is it?
Yeah, I think geologically speaking, it's loose, but models-wise, and they're not exactly parallel. At least all the figures I looked at, they're actually the flow lines sort of go up dip with temperature, meaning they slightly go to colder temperature and then they come back down. At least all the diagrams I looked at appear like that. Not that I understand exactly why.
One of the problems that they always do this with a kinematic model. In fact, the forces are oriented vertically. So
Yeah,
the slab
that's
is
right.
also rolling back, and it's sinking. So when things go down, something must come up somewhere.
Yeah, but I suppose the question is where, and whether that coming up somewhere is coupled to this flow or not, I suppose would be the
1400 C, is the potential temperature. Then, at some point it should connect to the ridge in the back arc, because We have a zero lithosphere thickness by definition, so I guess it should go up somehow. But
right. Mark?
First you said the models communicate.
that is not exactly what I said.
Cartoons can make even more things, believe me.
Yeah, so the cartoon there predicts a trenchward change in peak flow. Right? So, and at least in Cascadia and Alaska, it's unobserved. So the peak flow is very constant.
And as far as my reading goes, the heat flow data, I think, are poorly matched pretty much with even the newer models for most part, but I could get into trouble with it. What? The data is good. Yeah, the data are good. Right. Okay. Just to move quickly. So what I wanted to show you is, I think this figure gave us more trouble than anything, but but my point was to show that at least in mid to late 90s, early 2000, people considered these various dehydration reactions, and as a consequence, other communities worried about, okay, if you have hydrous flux coming off the slab, what are the different melting relations we should be worried about in mantle wedge when you have release of free fluid. And the thing, again, this also continues to be debated in experimental communities, where exactly is the solidus of peridotite in the presence of excess fluid. So H2O saturated solidus of peridotite. The most recent studies by Grove and his colleagues prefer a solidus like this, again, pressure increasing upward, temperature to the right. So again, the solidus is almost isothermal at around 800 degrees C, pretty much 3-4 GPa, the subarc depths. There were some other studies that preferred it to be around 1,000 degrees C, and there are differences between the two. But for most part, if it's somewhere around 800, 900 degrees C in the presence of excess fluid, the H2O saturated peridotite partial melt should be generated right above the downgoing slab, because, I'll show you some of the slab surface temperature predictions, but right above the slab you can get to temperatures at around 800. So if you have free fluid getting released from the slab, you should produce a hydrous partial melt, H2O saturated hydrous partial melt. But then the other thing to recall, again, mostly for the students here, but see how the solidus is changing slope here, or what's the slope of the solidus, at least between 4 GPa and atmospheric pressure here. It has a negative slope. So the Clapeyron slope here, del S over del V, which is the dP/dt of the reaction, it's supposed to be greater than 0 for all these anhydrous melting we talked about so far, these lines, but here it's negative. How do we reconcile that, or why it is negative? Do we know that? It eventually turns around and becomes positive. So we are all good higher up, but at lower pressure.
So basically, you have an isothermic reaction, because you have the sign of one of that, or the numerator or the denominator has to be negative.
Has to be negative. That's true. Which one is negative? The volume is negative. Entropy change for reaction is always positive. The volume change in this case is negative. But why? Yeah, so here on this side of these lines, you have a system which is peridotite plus free fluid, water. When you are melting, you are producing residual peridotite minerals and a hydrous partial melt. So just think of the volume change going from a pure water type of fluid to a partial melt. You have a negative volume change there, which dominates the negative volume change of the net reaction. As a consequence, this sign becomes negative here. Okay, so the peridotite partial melting in the presence of excess water can happen as low as this. If you have sediment or altered oceanic crust, that melting can happen even at a slightly lower temperature, like 750 to 800. So again, if you have excess fluid coming off the slab, your melting right above the downgoing slab can be generated very, very low temperature right above the slab. Okay, and based on these, many people have predicted models how, right above the slab, you initially generate a very low degree, extremely hydrous melts, and as you go farther and farther up, all the way to the core of the mantle wedge, probably just beneath the volcanic arcs, your extent of melting is much larger. The melts are now much more water poor. But these type of models are almost n-member models of water-driven flux melting, meaning water, almost as pure water coming off the slab, inducing hydrous melting, water-saturated melting, and that's the root cause of arc magma generation. However, there are other models as well. Oh, sorry.
At what point is water considered saturated, percent-wise?
That's a very good question. I would love to give you 1-hour lecture on what's saturated melting versus undersaturated melting, but it's a very good point. So people talk about wet melting or hydrous melting very, very vaguely. Most people in the community, they talk about it very vaguely. So depending on the depth where your rock is situated, you can add water to peridotite and either dissolve water only in the nominally anhydrous minerals like olivine, pyroxenes, or you can, by reaction with water, also produce some hydrous phases like amphibole or chlorite or serpentine, right? Any amount of water that is beyond the modal proportion of hydrous phase you can create, and accordingly total amount of water you can contain, or the solubility limit in the nominally anhydrous phases, if it's excess to that, your rock will be considered saturated in water. So in this case, it would be in these ranges. If you have 1% water in the system, I think you are saturated. But again, that 1%, the number I'm quoting, applies for peridotite. If you change lithology, let's say, for example, if you are dealing with a more potassium-rich lithology, like sediments or some altered oceanic crust, you may be able to create more micas, and as a consequence, the storage capacity of water may go up. So in order to saturate that rock, you may need more water. So depending on what rock you are dealing with, that limit will vary. But in this case, people are considering sort of hydrous melting purely by a fluid-saturated melting. However, there is also another effect of water, which is not just creating that really low solidus, but actually creating a melt fraction temperature trend that is situated at a much lower temperature compared to the dry melt fraction temperature trends. So there is a delta T between the dry TF trend and water content, and as you have more and more water dissolved in the basalt, that TF trend of melt fraction and temperature is shifted to lower and lower temperature, and that's exactly shown here. The delta T, which is the difference between the temperature melt fraction trajectory of dry melts versus the temperature melt fraction trajectory of wet magmas or with different amount of water content, that delta T increases with increasing amount of water in the melt. In other words, if you want to produce a basalt with around 5% water, you can produce that basalt by producing a hydrous basalt at temperature around 150 degrees C lower than the dry TF trend. You don't have to be at the fluid-saturated solidus. Fluid-saturated solidus is at 800 degrees C, much lower temperature. But the basalts that are produced actually are with, let's say, on average 5% or so. They are produced at not 400 degrees or 500 degrees lower in temperature from the dry solidus, but produced more or less like 100 to 150 degrees at most. Doug?
Yeah, 2 drops, really low solidus was a little bit controversial, I think.
Yeah, I think a little bit would be an understatement. It's a lot controversial.
Is it generally accepted in your community?
No.
No.
Even less accepted in my mind, but that's my bias. But yes, a question? Oops. Don't send the link to Tim. I mean, come on.
So what do you think it is if it's not that low?
It's probably closer to 1,000 now that I have said it. So I may as well go all the way. Yeah, I think it's, it's controversial for a reason, because these are determined from what we call these quench experiments, and it's very difficult to interpret the product of high pressure, high temperature quench when the melt is extremely hydrous. You can find all sorts of residues in your experimental capsule that you can interpret as a product of quench from a melt or quench from a vapor. It's a messy, literally a messy business. So yeah, so I give them room. Yeah, they could be right as well. Mark.
Question is drawn mostly from deformation experiments on olivine. So when you have water to olivine, you're doing deformation experiments near their melting temperature. Some of the water gets between silicon and oxygen bombs to change the melting temperature. A lot of the water actually just gets in the interstices in the olivine structure. So when you say 1% saturated, how much of that is actually making the silicon oxygen bonds weaker, and how much is?
So when you talk about silicon-oxygen bond, it's in olivine? Oh, okay. So again, the olivine's water solubility limit varies as a function of pressure, but at around 3 GPa or so, I would believe it's no more than 1,000 ppm water in olivines.
But dissolved water in crystals, when you're melting them, if that's all getting involved in the structure, or is some of it just stuck in?
Well, if you are doing really fluid saturated melting, you have all your nominal anhydrous minerals at the saturation limit. Let's say 1,000 ppm, CPX would have even higher, maybe 2,000 or so. But on top of all these water dissolved in minerals, you also have a free fluid. That's causing the fluid saturated solidus to be at 800 to 1,000. Okay, I think I'm running out of time. But another evidence of this water present melting, or at least the influence of water on creating more F, or larger melt fraction, comes from the geochemistry of basalt. So one example people used over and over again is looking at the titanium content of basalts. Again, titanium being an incompatible element, enters the melt phase. So if you have any agents that can cause larger extent of melting, that will lower the titanium content of the melt. Again, just go back to your batch melting equation. So if you have more water in your primary basalts, you will create, because water is an incompatible element, it will create more F, and as you have more F, you will dilute Cl, and overall, based on all the primary melt inclusion data and so on, we do see a negative correlation between titanium content of basalts and primary or near primary water content of basalts. So overall, I think it's pretty well established that water does influence the melting systematics. What's debated is whether the H2O saturated solidus is of that much of an importance versus whether it's just water getting added and influencing the melting in a relatively hotter part of the mantle wedge beneath volcanic arcs. And I think we already sort of touched on many of these. More recent models, at least based on my readings, are trying to get into the details of the slab PT path, slab surface pressure temperature path. They're taking into account the seismogenic zone, sort of more of a completely decoupled zone here, a partially coupled zone to account for the stability of the cold nose, and then a fully coupled viscous coupling of the slab surface and the wedge. And the reason I sort of show this, although it's not so-called petrology, is that how these different treatments are done are extremely critical in terms of producing the slab surface pressure temperature path, which in turn is extremely critical in predicting what sort of fluid will come off the slab. Is it hydrous fluid versus hydrous melt, and so on. Another difference that, again, is gaining more traction for the last 10 years is people have been, at least the modeling community has been moving away from the isoviscous mantle wedge rheology to more olivine-like temperature and stress-dependent rheology, but again, still mostly dry olivine, to my knowledge. And what that's doing is it's creating much better viscous coupling between the downgoing slab and the mantle wedge. And as you can see, these are various isotherms. Depending on where the decoupling zone is between the upper plate and the downgoing slab here, you can create a temperature that is getting much more quickly hotter at a given depth than if you were assuming isoviscous sort of mantle rheology, and that gets that has a lot of influence in predicting the dehydration or devolatilization reactions for the downgoing slab materials. Here is one example from a relatively recent study of Ellen Syracuse in 2010. As you can see, given the fact they are putting the complete coupling zone at around 80 kilometers depth, and that sort of olivine-like rheology in the mantle wedge, the slab surface pressure temperature path has this really strong temperature gradient at around this depth. In other words, the top of the slab goes down and increases in temperature, but increases in temperature very, very suddenly, and then reaches this. What are shown here in the background are various contours of water content that can be retained in altered oceanic crust. As you can see, you can dehydrate your altered oceanic crust tremendously if you reach 100 kilometers depth or so. And not only that, on top of this, I don't think you can see it very clearly, these solid or dashed white lines are water-saturated solidus for altered oceanic crust and sediments. And what you notice here, not only these different dehydration boundaries are crossed, if the slab surface pressure temperature paths are that hot, you actually also cross the hydrous or the water-saturated solidi for sediments and altered oceanic crust. In other words, if this is really the case, and if you have a source to supply a free fluid or H2O-rich fluid, you will not just create an H2O-rich fluid, but you will actually create a hydrous partial melt. Okay, and that's what is shown here. The solidus, if it is here, the H2O content of the fluid is actually much lower. So in other words, your fluid is actually probably a partial melt. But the caveat is you need to have a source of a free fluid phase, and that may or may not be the case. The final thing that I would quickly like to touch on is there are also recent models that predicted that if you just below the arc front, where melt is supposed to be segregated, the temperature is thought to be high enough that although you may create this water-saturated hydrous partial melts of the top of the slab, but the temperature here is sufficiently high that it can create partial melt even if your mantle was nominally anhydrous, meaning not completely anhydrous, but a mantle with maybe 100 to 200, 400 ppm water, not a free fluid phase. And it's consistent with what we understand how water depresses the solidus of mantle peridotite, even with trace amount of water. In other words, even if you do not have tons of water so that you would saturate with a free fluid phase, but if you have 50 to 200 ppm or maybe up to 500 ppm water, the solidus of mantle peridotite is actually or can be lowered by 40 to 100 degree C. And this sort of goes back to, Roberta, your point about how water depresses solidus for a nominally anhydrous mantle. This has been talked about for applications beneath mid-oceanic ridges, but it's also relevant for beneath subduction zones where water can influence melting, but not by saturating the peridotite, but by creating or shifting the solidus maybe by 50 to 100 degree, not more than that. The final aspect, which is again just something to think about down the line when we think of research projects. Another thing that came up more recently in various dynamics or geodynamic literatures is the contribution from the slab not by releasing hydrous fluid and not by releasing hydrous partial melt, but by actually detaching some sediments or even altered oceanic crust from the downgoing slab. So instead of the whole slab remaining as a coherent body, because the densities of many of these sediments that are on top of this downgoing slab have densities lower than the overlying mantle wedge peridotite or Herzbergite, they can actually physically detach. And if that's the case, you can actually physically transport some sedimentary diapirs or blobs into the hot mantle wedge. If their dimensions are small enough, they would also partially melt, not on the slab surface, but in the mantle wedge. And that can also contribute to melt composition and so on. But I think with that, I'll stop and take more questions and discussion.
Thanks a lot, Mark.